I'd like to introduce our speaker today, Arjun. Arjun graduated from Columbia's undergrad last summer, and
Awesome. Thanks, Shri. Hey, folks. Thanks for attending today's talk. It's the first SPS talk of the year and my second talk at SPS. My first talk was on quantum computing last year, but this one is completely different. It's going to be on heavy ion collisions and the gauge gravity correspondence. Let's start off with a little bit about me. I was a physics and math undergrad at Columbia, and I graduated in 2023. I did some research at Columbia on heavy ion collision experiments with Brian Cole, and I also wrote a senior thesis in mathematical gauge theory with Mike Miller. Brian is a heavy ion physicist. He is currently conducting research at CERN this year, and Mike Miller is a topology mathematician who's now an assistant professor at the University of Vermont. Currently, I'm a master's student. I'm studying the Part 3 in mathematics at Cambridge University and an incoming PhD student at MIT. My current work is on heavy ion collision theory, and I'm working with Krishna Rajagopal at MIT to study heavy ion collisions using something called the gauge gravity duality. And that's the topic we're going to talk about today. So here are the topics we're going to cover. We're going to talk first about physics at different scales, and then an example of physics at different scales. This example is going to be heavy ion collisions. Then we'll see how we can treat physics at different scales within heavy ion collisions using a hybrid model developed by my research mentor Krishna and his collaborators. It uses the gauge gravity duality. And finally, I'll share some ways you can learn and get involved in this flavor of work at Columbia. Cool. Let's talk about physics at different scales. We have axes of length, mass, and speed. The negative axis here indicates when these quantities go to zero. They don't become negative. And we have different versions of physics to describe nature in each of these sectors within this chart. So let's go through these sectors. Can anyone tell me which version of physics is used to describe physics in the low mass, high length, and low speed regime? Yeah, exactly. It's Newtonian mechanics. You have time and space being absolute. You don't need to keep track of really small length scales and quantum mechanics. What about at really high speeds? Which type? Yeah, exactly. It's special relativity. So Einstein came along and said, what happens if we travel really close to the speed of light? He found that Newtonian mechanics breaks down and you need to treat it with special relativity. What about the high mass regime? Yep, it's general relativity, because gravitational effects in this regime are large. Okay, now what about high mass and high speeds?
Is it also just GR?
It's also just GR. Do you know why?
GR works.
True. GR also works with high speeds because special relativity is just a special case of general relativity. Cool. Any questions so far? Have I lost people? Okay, great. Oh, by the way, if anyone has any questions at any point, feel free to just throw them out there. Okay, now what about this octant of low length scales, low mass, and low speeds? Yeah, exactly. It's quantum mechanics. You're looking at the scales of atoms, which have low sizes and mass, and they're not moving around super fast. But now let's say they do move around super fast, like in particle colliders. What theory of physics describes them now? Precisely. Quantum field theory is used here. You describe particles in terms of their fields, and they obey certain quantum mechanical laws. Now, what about the low length and high mass regime? It has to be some version of GR and quantum mechanics. Yeah? Quantum gravity. Awesome. I love that you said it doesn't exist. Technically, theories of quantum gravity exist. String theory is a classic example, but these theories haven't been proven in experiment yet. Finally, what about this octant where you have quantum gravity at high speeds? Yeah, we also call this sector of physics quantum gravity. In this sector, GR and QFT have to coexist. Okay, now what's the point of all this? This image is to show that we use different theories to describe physics effectively at different scales. This is going to be a very powerful statement when we study heavy ion collisions. But before we get there, are there any questions? Have I lost people? Cool. Now let's talk about heavy ion collisions. Heavy ion collisions involve smashing particles together at really high speeds. So we're talking about the physics at low length scales of particles at really high relativistic speeds. So our discussion will focus on the physics within this region here, the quantum field theoretic region of this chart. Although this exact picture of scale separation in physics won't be used, it is a good heuristic that introduces us to the idea of scale separation. In fact, even within the regime of quantum field theory, we will need to rely on physics at different scales of another quantity that we'll call the gauge coupling. But before we say more about that, let's understand the objects we're going to be working with. These objects are quarks and gluons. In a heavy ion collision, we're colliding heavy ions, so they're nuclei. These nuclei are composed of protons and neutrons, and protons and neutrons are themselves made up of quarks and gluons. You have 6 quarks: up, down, top, bottom, strange, and charm. It turns out that you'll never find a quark alone. You'll always find them in pairs or triplets upon measurement. We call these confined pairs and triplets of quarks hadrons. For some further terminology, we call triplets of quarks baryons. Some examples include protons and neutrons themselves, and any pair of quarks we call mesons. Yeah? Good question. There is not. In fact, this is such a good question that if you answer it right, you get $1 million. It's been one of the Millennium Prize problems. There are 7 of them, of which 1 has been solved. The name given to this particular problem is the mass gap problem. Basically, it asks, why do we find quarks confined in pairs or triplets? You might ask, okay, what happens if we pull 2 quarks apart so that we try to measure them when they are decoupled? Well, it turns out that if you pull them apart far enough to measure them independently, their energy configuration is so high that it becomes energetically more advantageous to just create a new pair of quarks and attach them to the original ones. So if you keep pulling quarks apart, you get a shower of quarks between them. This happens during a nuclear collision, as we'll discuss. A great question. Any other questions about this? Yeah?
Why is 3/4 the stable structure and not like 5 billion?
That's a good question. It has to do with some algebraic properties of the colors of quark configurations, and also a rule that the confined states of quarks have to have an integer value of charge. These quarks have a fractional number of electric charge, so when they're confined into hadrons, they have to sum to an integer value of charge, because that's exactly what we measure. So for example, the proton has an integer value of electric charge +1. You could create quark configurations with 4 or 5 quarks that satisfy these properties as well, but they decay almost immediately after creation in an experiment. These questions surround one topic, quantum chromodynamics. We have 4 forces of nature: the gravitational force, the electromagnetic force, the weak force, and the strong force. And the strong force is described using quantum chromodynamics, or QCD. Why chromo? Just like the theory of electric charge is described by quantum electrodynamics, the theory of color charge, the charge held by quarks and gluons, is described by quantum chromodynamics. In electrodynamics, you have electrons and positrons as charges, while photons mediate the electromagnetic force. And in chromodynamics, quarks are charged with color, while gluons mediate the strong force. However, a key difference between QED and QCD is that photons are not electrically charged, while gluons are chromatically charged. This results in some interesting phenomena that makes the physics of QCD very different from the physics of QED. Finally, there's a mathematical difference between these two theories that we won't describe in detail, and that's the gauge theory description of the two theories. QED is a U1 gauge theory, while QCD is an SU3 gauge theory. These U1 and SU3 are what we call gauge groups. These gauge theories have to do with the symmetries of particle fields within each of the theories. And what this means is not important to us in this talk, but the number 3 here in the SU3 gauge group of QCD will be important. So keep that number 3 in mind.
That means that QCD actually doesn't, gluons move at a speed less than c, because if they have charge, they have mass, and if they have mass, then they can't.
Not quite. Particles that have charge don't necessarily have mass. Gluons are in fact massless, and so can move at the speed of light. Any other questions? Cool. Many of the questions surrounding quark confinement, the strong force, and more properties of QCD give us a good motivation to study it. And one way we do this is using heavy ion collisions. Okay, let's say we take two heavy ions, like a lead ion and another lead ion. They're made up of protons and neutrons, which are themselves made up of quarks and gluons. Let's smash them together at really high energies, like at facilities like the Large Hadron Collider. My collaborators, research mentors, many professors here at Columbia, and I conduct research using LHC data. When we collide these particles together, they rarely overlap exactly. Instead, they overlap in an almond-shaped region, as you can see here. We're looking at the collision facing the direction of the beam of heavy ions in this image. And what do we see here in this region of overlap? We see a soup of deconfined quarks and gluons moving around and bumping into each other. This phase of matter is what we call Quark Gluon plasma. It turns out that this phase of matter is the original liquid that filled our universe microseconds after the Big Bang. It's the origin of the particles we see today. And after quarks and gluons exited this primordial liquid, they reorganized themselves into hadrons through a process called hadronization to give us the hadrons we observe around us today. This phase of matter is also the hottest liquid and the most liquid to have existed. Basically, it's a frictionless liquid of quarks and gluons. I think this slide contains some of the coolest properties of quark gluon plasma, and it's 100% a motivator for why we are interested in studying QGP. Okay, let's dig deeper and understand the physics of QGP. It's a highly viscous fluid in which quarks are deconfined but still interact. What does this mean? Basically, the quarks within quark gluon plasma are not bound solely to one or two other particular quarks, but rather they interact with many quarks simultaneously. Furthermore, these interactions are quite strong. We characterize the strength of these interactions using something called a coupling constant. When this constant is on the order of or greater than 1, we say our theory is strongly interacting. The consequence of this is that calculations of such a theory become unsolvable by standard perturbation theory techniques. This is the most important point of this talk. The unsolvability of perturbative calculations in a strongly interacting theory motivates the need for some non-perturbative methods. The one we'll look at is the gauge gravity correspondence. We'll get to that in a bit. before we do that, we need to understand what object we need to use to probe the strongly coupled physics of QGP. The probes we'll use are called jets. Jets are sprays of particles that shoot out of a quark gluon plasma. So in this image, here's a jet. Let's say it's produced by a quark. It undergoes a process from its inception in the plasma to its detection at the edge of a particle detector. Here's what happens. First, a collision takes place. Quark gluon plasma is formed, and a jet begins shooting out of the plasma. Then, as it traverses the plasma and exits it, the jet fragments into a shower of partons. Remember how I said when you split two quarks apart, they fragment into a shower of more quarks? That's what's happening here. This fragmentation process creates additional particles, quarks and gluons, we call them partons, so that the system reaches a lower energy state. Keep in mind this fragmentation process happens both within the plasma and outside it. Once the jet is out of the plasma, it starts to hadronize into confined pairs or triplets of quarks. These hadrons are then detected and grouped together using algorithms that reconstruct and describe the physics of the original jet. Okay, since jets store information like energy, momentum, angular distribution, multiplicity, and structure, they make fantastic probes of the QGP.
Why is it that if we're able to make a quark gluon plasma by smashing a bunch of protons together and measuring the angle and energy at which they're ejected, why does that count as disentangling?
This is a great question, and it gets at the definition of deconfined. These quarks are deconfined within the plasma in the sense that you can't pinpoint distinct pairs or triplets of quarks that are bound together. Rather, all these quarks are interacting with each other at different moments in space and time. Rather than being deconfined in the sense of being alone, I would think of them as being deconfined in the sense of having multiple partners to pair up with. What we're really interested in here is the process by which jets redistribute their energies across their lifetime, from scales of the QGP to scales of hadron detection. This is where the idea of different physics at different scales will come into play. Now, there are multiple ways to calculate the observables like energy, momentum, etc., theoretically. One such way is using a technique called lattice QCD, which is really good for studying QGP formation and thermodynamics. However, it's not as great for studying the dynamics of these jets. That is, for studying how they lose energy or hadronize. A professor at Columbia who works on lattice QCD is Norman Christ. He does take undergrads for research, so if you're interested, you should reach out to him. Another method we use to study quark gluon plasma is using perturbative QCD. Remember how I said perturbation theory doesn't work so well because QGP is strongly coupled? This makes perturbation theory a wrong approximation of QGP. However, it's the right theory because it is a theory of quantum chromodynamics. The physics is correct, even though the math is not. So here's our question. Is there a theory that will help us study the hydrodynamics of this strongly coupled plasma? Okay, we'll need physics that deals with both the strong and weak processes involved here because of the different scales we're working at. First, hard jet evolution, like fragmentation, is described using weakly coupled physics and can be treated perturbatively. That is, you can write out the Feynman diagrams for each of the fragmenting scattering processes. And hard jet production is also weakly coupled since it's the result of scattering between the original quarks and gluons in the heavy ions. But then you see that these jets have to interact with other particles within the QGP. The QGP is itself strongly coupled, and the interactions of jets within the plasma are strongly coupled too. This means that we need a hybrid model that treats the weakly coupled physics of jet production and hard jet evolution, as well as the strongly coupled physics of QGP and its interactions with jets simultaneously. This model was developed by my research mentor, Krishna Rajagopal, and his collaborators in 2014. In this hybrid model, it's simple enough to treat the weakly coupled physics using perturbation theory, but how do you treat the strongly coupled non-perturbative processes? Any guesses? What have I not talked about so far? Yeah.
Brought up your gauge gravity.
Exactly. We're going to use the gauge-gravity duality to help us treat the strongly coupled physics here. Okay, the gauge-gravity duality is an equivalence between particle theories in 4 dimensions, 1 time and 3 space, and gravitational theories in 5 dimensions. There's a lot of math within this equivalence that I'm not showing here, because I'll go more into detail on the math side next week at the Undergraduate Math Society, where I'll be giving another talk there. At that talk, you'll get a glimpse into why we think this equivalence should hold. We also call this duality the gauge-gravity correspondence, or the ads-cft correspondence. A CFT is a conformal field theory. It's a type of quantum field theory that looks the same at all length scales. And ADS here stands for anti-de Sitter. It's a type of spacetime with constant negative curvature. The gauge-gravity duality was first proposed by Juan Maldacena in 1997, where he proposed a more precise description of this duality using supersymmetric field theories and gravitational string theories. In particular, he proposed a duality between an n equals 4 SUN super Yang-Mills theory of four supercharges in 4 dimensions, and a type 2b string theory in ADS5 times S5. Although it's not important to understand what these theories mean exactly, it is important to recognize that a supersymmetric Yang-Mills theory with gauge group SUN and 4 supercharges, that's the n equals 4 here, that theory is a conformal field theory. And it's dual to this stringy gravitational theory. Okay, looking around the room, I know I've lost some folks. Can you guys please tell me where I lost you?
Yeah.
So basically what's happening here is that we take a 4-dimensional gauge theory of particles at some energy scale, and then we ask what the theory should look like at another energy scale, like a higher one. We keep asking this question and create a stack of such theories at all scales of energy. This stack of 4-dimensional conformal field theories forms a 5-dimensional space-time. And you can write down a metric for the space-time, which turns out to be the 5-dimensional metric that satisfies some required symmetry laws, like Poincare symmetry and 4-dimensional conformal symmetry for each of these slices, for each of these 4-dimensional conformal field theories. And it turns out that this 5-dimensional metric, if you take these symmetry laws into account, is a 5-dimensional ADS space-time metric. So this 5-dimensional space-time is a space-time with negative constant curvature. We'll see the math behind this idea at next week's math seminar, so stay tuned for that. And I'll give you guys the details for when that seminar is going to take place at the end of this talk.
So a lot of our observations have point us towards space time or the curvature being almost flat, like negative curvature. So even if that disagrees with that, it still helps predict. What I'm saying is how does that reconcile?
You're right. Our universe is not anti-de Sitter. However, this ads-cft duality doesn't assume that. It says nothing about the nature of our own universe, but rather says that if you have a conformal field theory of nature, then it's dual to an ADS theory of gravity in one higher dimension. It's an equivalence between mathematical objects, theories of some nature, not necessarily our nature. In this talk, we intend to use this duality not as a way to understand the geometry or stringy nature of our own space-time, but rather as a tool to perform what would otherwise be hard calculations of particle phenomena in the easier gravitational dual, as we'll see shortly.
Why not just treat gravity as if it's a quantum field and use a slightly better version of a quantum field of gravity? Why string theory specifically? You can use loop quantum gravity, you can use kind of the other ones, or you could literally just treat gravity as its own field in QFT. Why not do that?
Yeah, the important part about this theory of quantum gravity, to us, for the purpose of this talk, is not the mechanism that describes this theory of gravity. Rather, it's the notion of a duality. And dualities are of particular importance in any field because they typically allow you to cast hard problems on one side of the duality and to easy problems on the other side. So you could describe quantum gravity using another theory if you wanted, but that's not our goal. Our goal is to make our lives easier when computing strongly coupled physics. And on the next slide, we'll see how this duality does the trick.
And what's N?
N sub c here is the number of colors in your theory. So if you recall, QCD has 3 colors, so it's an SU3 theory. NC in particular is important here because this duality simplifies when we take NC to infinity. We call it the large N limit. So if we have a theory with infinite number of color charges, this duality simplifies. Any other questions? Okay, so why is this important? It turns out that difficult calculations in strongly coupled gauge theories of particles becomes easy in the weakly coupled gravity dual. In fact, if the number of color charges is large and your coupling is strong, the gravity dual becomes a theory of classical supergravity. This makes calculations quite easy to carry out. We can apply this idea to the hybrid model. Returning to it, recall that we treat the weakly coupled physics of jet hydrodynamics perturbatively, and now we treat the strongly coupled physics using the gauge gravity duality. Essentially, we perform hard calculations in the strongly coupled limit using easier calculations in the weakly coupled gravity dual. How do we do this? 1, we find the gravity dual of QCD. The second thing we do is describe our particles using strings in the 5-dimensional spacetime. And the third step is to calculate the observables we desire, like energy and momenta of these strings. Okay, easy enough. But there's a catch. Finding a gravity dual of QCD. We haven't found one. A first hurdle to finding a gravity dual of QCD is the fact that there are only 3 color charges in QCD, whereas the gauge gravity duality simplifies to a classical supergravity theory only in the infinite color charge number limit. A more significant issue, though, with QCD is the fact that it's not a conformal field theory, and it breaks down at low energies. This is why we don't understand quark confinement, a phenomenon that occurs at low energy scales. So it's harder to think of an ADS dual for this non-conformal quantum chromodynamic theory. How do we solve this? We solve it by performing calculations in a different kind of plasma. Instead of calculating quantities like energy loss in a QCD plasma, we calculate them in an n equals 4 supersymmetric Yang-Mills plasma. This, if you recall, the n equals 4 SUN supersymmetric Yang-Mills theory is a type of gauge theory with 4 supercharges, and it's a conformal field theory with the type 2b string theory dual that we saw a few slides ago. You might be thinking, well, what's the point of doing this if it's not QCD? It turns out that the hot, strongly coupled liquid phases of the n equals 4 SYM theory and the QCD theory are more similar to each other than their vacua and low energy physics, that problematic energy sector that's not conformally invariant. So calculations of jet observables in an n equals 4 supersymmetric Yang-Mills plasma might give us some useful insights into the physics of QGP itself. However, there are some important caveats to note. We already mentioned that QCD has 3 colors. However, we take the number of colors to infinity in our n equals 4 SYM plasma. Additionally, QCD is not conformal, while n equals 4 SYM is conformal. Another important difference is asymptotic freedom. The QCD coupling decreases, that is, it becomes weakly coupled, as the energy is increased to infinity. However, since n equals 4 SYM is conformal, it remains strongly coupled at all scales. This is not too big of an issue because the QGP we study in nuclear collisions is not close enough to the energies and temperatures at which the QCD coupling becomes weak. Finally, the two theories differ in terms of their fundamental and adjoint degrees of freedom. What does this mean? It means that even though studying jet observables in an n equals 4 SYM plasma can give us insights into jet physics in quark gluon plasma, we must only treat these insights as qualitative and not quantitative. Okay, now we have a third way of calculating jet observables, using the hybrid model of strong and weak coupling. It uses holography, another word for the gauge gravity duality, and it's the right approximation because it treats both the strong and weak coupling scales of physics simultaneously. However, it is the wrong theory of QGP. It uses an n equals 4 supersymmetric Yang-Mills plasma rather than a QCD plasma. Any questions? Cool. Okay, so what does the hybrid model approach to calculating jet observables actually look like? We first cast particles like quarks and gluons into strings that fall from the boundary theory of our 4-dimensional physics into the bulk of our 5-dimensional gravitational spacetime. We then calculate the drag experienced by these strings and equate it to the energy loss quarks experience as they traverse the QGP. We feed this energy loss as a parameter into a Monte Carlo simulation of collisions, run the simulation, and use the output data to find jets from each collision. We can then manipulate this data to calculate jet observables. One such observable shown in this figure here is the nuclear modification factor, and it's a way of measuring energy loss of jets in heavy ion collisions. More specifically, it's the ratio of the number of jets with certain energies in heavy ion collisions to the number of jets with those energies in proton-proton collisions. In this figure from 2014, we see qualitative agreement between the hybrid model calculation in red and the measured values of the nuclear modification factor in black. In this case, there's a weak dependence on transverse jet momentum in the nuclear modification factor in both the data and the hybrid model calculation. Finally, there are other steps involved in hybrid model calculations, including the physics of wakes left by jets as they traverse the QGP, the effects of elastic scattering, and jet evolution using an algorithm for jet fragmentation called DGLAP. Yeah.
So, how, if at the end of the day, you're like looking at this qualitative shape of like a certain observable that is like the result of some experiment that had all this like weird cone reflection thing and the LHC, right? Like, how many different shapes really are there? You know, like, it's because I guess more generally, I'm asking, like, at the end of the day, like when you get back those sorts of results and like go to publish, right? Are you attempting to make some assertion about, you know, the relationship between the combination of theories you cooked up and then like reality? You're like, oh, we predicted something sort of non-trivial about real life because of all these dualities we identified. Is that what you're trying to say?
Yeah.
And if so, then like, you know, it seems like there were a lot of steps, and it seems like there aren't that many like qualitative trends to really pin down, right? Like,
The main theme to look at here is separation of scales. We're trying to approximate the observables for jets in a hot, dense plasma that enjoys different physics, different couplings at different scales. The treatment of multi-scale physics is the key idea behind the hybrid model. The specific theory of physics we use doesn't matter to the hybrid model. We could use some other gauge theory that has a known gravity dual and perform our energy loss calculations in that gravity dual. In fact, if you do find a weakly coupled gravity dual for QCD, then the hybrid model would be a fantastic tool to calculate jet observables in the actual QCD Quark Gluon plasma. This is because it would then be the right approximation at different coupling scales with the right theory of QCD physics. All right, now for the final slide. How can you get involved? Basically, I'll upload a bunch of resources, including a link to this recording, these slides, and references you can use to learn more about heavy ion collision physics and the gauge gravity duality. I'll also list some professors at Columbia who conduct research in this field, so you can get involved in research at Columbia if you'd like to do so. Finally, here's the information about the math talk, where I'll discuss in more mathematical detail the ads-cft duality. It'll take place next week, and most importantly, food will be provided. Thank you so much to everyone for attending, and thank you to SPS for hosting. I'll stick around for a while if anyone has any questions. Thanks so much again.
Because I remember